Hello. So this is the demo for neural network from scratch notebook. Uh, so so in this we will just dive into deep learning fundamentals and the neuron activation function, forward propagation, loss function, back propagation, building the network like that. So yes, the first is the neuron. So a biological neuron receives signal from dendrites and processes them in a cell body and sends output through the axion. We model this mathematically. So we have input x1, x2, x3, and it goes through weight 1, weight 2, weight 3, and then some bias is added, and then it goes to an activation function and we get an output. So the mathematical form for this is this. We just sum all the weight, we just multiply weights with the input vector and sum all the all the inputs and weights, and then just add bias to it, and that then the value is then passes through an activation function to add a non-linearity to it. So yeah, let's build a single neuron is just one weight when there are no layer, nothing, just one input matrix and one weight and the bias, and then passing it through an activation function. So if a weight looks like this input looks like this, the weights look like this, we have the bias, we just multiply these two, add them, basically dot product of these two vectors, and then multiplying with this, adding with this, so we get this. So this is a single neuron's output. This is without activation, that we have not put any activation. The step 2 is adding activation function basically adds a non-linearity. Without that, it will just all the operations will just collapse into one single transformation. So yeah, without activation function, a neural network will just be a series of linear transformation. No matter how many layers, the output still be a linear function of the input. So activation function introduce non-linearity, allowing network to learn complex patterns. So there are different types to it: sigmoid, tan, ReLU, leaky ReLU, and softmax. We have gone through details in the previous videos. I'll not give the. So yeah, for this sigmoid, we just there are different functions for it. Excuse me. For sigmoid, we are calculating the sigmoid with on our own. For tan we are using NP, numpy tan. ReLU is maximum of 0 or the value, leaky and softmax. Then let's visualize them. So sigmoid is 0 to 1, tan is -1 to -1, ReLU is 0 or max of x. Leaky ReLU, it allows some negative value. Then we have loss functions like mean square error, this is for regression, binary cross entropies for binary classification, categorical cross entropies for multi-class classification. So how do we call it? We just apply the formula over here, the formula which we learned. So this is what we are doing on our own, but we can always use the inbuilt functions which NumPy and TensorFlow, PyTorch have. Mm, yeah. Yeah, so this is the mean squared error. We just have to find the value with the least error, and the that will be our predicted value, because we don't want to have a lot of variance in that. Then let's move to we just saw singular layer, let's move to a fully dense layer. So we have um, a dense layer connects every layer of input to every neuron. Okay, yeah, this is the dense layer. So every input is connected to each neuron. That's why it's called dense. uh, so yeah, the implementation is same as that. Then we have this back propagation. So that was the forward pass which we saw. Now back propagation is the main step in the learning. So it is, it tells you how much each weight, how much we should change the weight with respect to the loss which we have got. So back propagation, it's mostly d by dl by d by w is d by dl by d by a, d by a by d by z, d by z by d by w. So if forward passes x go input and then multiplied with the vector weights and bias, adding bias in this, and we got this output. Now how much the output changes with respect to the weight is how much the output changes if we change the z, which was the output of this. But how much does this change is dependent on how much uh, L is changed when we change A. And this is how the back propagation works. So it is just the implementation of that. So we have Adam optimizer. So adaptive moment estimations, this is the most common, most popular one. It combines momentum and RMS prop, which is second moment estimate for. We have to pass the learning rate to it. So and this is how the multiple layers look like. So fully connected is each layer connected, each neuron is connected to every neuron in the next layer. Then we have this neural network feed for the whole neural network, feed forward neural network built from scratch. So here data flows from right to left and gradients flow from right to left to right, forward flow, data flows left to right and gradients from right to left because we are back propagating change. So yeah, this is the example. We are just creating a neural network. The loss is mean square error and we are using Adam gradient. We have created a dense layer with the activation of ReLU and another layer with sigmoid, and yeah, so this 2 is basically size of input and 1 is size of output. Then we're just fitting it for 10 epochs, 100 epochs, and so initially it will just initialize the layers, and in the forward it will call the propagate input through all layers, and in the backward it will do the it will compute the gradients for all layers, and this is where the learning happens. So first it will compute the loss gradient with respect to output and then propagate gradient backward through layers. So each layer computes its own weights and gradients, and then we will just train the neural network. This is where the training loop will come, where we'll set the gradients to 0 in the initially, and then because in each epoch I want the gradients to set to 0, and then yeah, training the data. So in the predict we will just call the forward function, and yeah, that is it. So X learning XOR is the classic challenge. XOR is a classic problem that single neuron cannot solve because it's not linearly separable. This is why we need hidden layers. So XOR is basically, uh, if the output inputs are same, then it's 0. If the inputs are different, then it's 1. And it is very difficult to find out using a single neuron, a single layer. So a single neuron. So that is why we need, multiple layers for. Yeah, this is just an example to show how neural networks actually work. So we just trained the model to solve the XOR problem, and here you can see we have two layers, and with just 33 parameters, and this is the loss function and the gradient we used. And this is the loss. The accuracy was 100%, as you can see, and the loss drastically dropped. And this is the graph for epoch versus accuracy, and the accuracy increased right away. And this is how the XOR boundary is formed for both the four outputs. Now let's see the binary classification, the Moon's data set. So here also you can see the red is the training loss, and blue is the training loss, red is the validation loss, and this is the AUC curve for both the training and validation. And the Moon's data set, as you can see, it very efficiently drew the difference between both the sides. So this is a very complex problem, and finding this out using a normal statistical model is difficult, and this is where neural networks shine. They can handle the complex patterns in the data, like the spiral problem. So as you can see, the accuracy really nearly touched 0, and sorry, the loss touched 0, and accuracy was almost 100% after training. And this is how the boundaries are not very, very efficiently it did that. And we have seen that it's very difficult to do that using statistical models. And again, this is another example using the MNIST image data. And image data, as we all see, we can see that it's complex. It has a lot of spatial information and things like that. But neural network is able to find those patterns, those complex patterns which are in very high dimensions, and it is able to predict it. Again, the same thing. Yeah, that is pretty much it. Thank you.